You can start.
Okay. Hi guys, I'm Rajendra. Today's session is binary heap. Though I said it is heaps, I'm only going to cover only one type of heap, which is binary. And there are other type of heaps like leftist heap and other things. You can go to Wikipedia and find that out. I'm just covering only one type of heap, which is binary heap. So what is a heap? Heap is a non-linear, a tree-based data structure. It is a complete binary tree, and we implement it using a simple array, a dynamic array. Let me share my screen. Okay, are you guys able to see my screen?
Yes, OneNote.
Yes. Okay, nice. Yeah. So, yeah, as I said, heap is a nonlinear data structure, but we implement using a simple array. Most of the time, people get confused, or it is very synonymous with the concept priority queue. What is the difference? Priority queue is an abstract data type, whereas heap is a concrete implementation. So, I mean, in other words, priority queue is the concept and heap is the implementation which runs. The heap does have the capability to take into account a priority order. So very naively, we can say priority can be a minimum of 2. Minimum is the priority. Then in a heap of elements, whoever is the minimum of all of them, that becomes the top of the heap. That remains at the top of the heap. So similarly, for max heaps, the maximum of the bunch comes to the top. So when I think about heap, we can simply imagine about a heap of stuff. It is a pile of stuff. What is on the top is determined by the priority that is used to build that heap. Having said that, so let's see one example of a max heap. So the heap property basically says the root or the parent should be bigger than its immediate children and recursively. So what I mean by that is 97, because it is max heap, it is bigger than 93 as well as 96. 96 in turn is bigger than 81 and 74. Similarly, it goes. This is a max heap. You can just see it is a recursive data structure, so to say. One interesting thing you will notice, the 81 here in this particular section of the thing, the 81 here is on the left. If it were a binary search tree, of course it is not a binary search tree. That is what my point is basically. If it were a binary search tree, we would expect the 74 to be on the left and 81 to be on the right at least. So this thing is not a binary search tree.
And does it need to have like 2 nodes only?
No, there are times when a node will not have a right child. So the only requirement, because it is a complete binary tree, so the difference between complete binary tree and full binary tree is the one that I'm showing right now is a full binary tree. It has 1, 2, 3. So 1, 2, 3. Its height is 3, and as you can see, it has got how many? I believe it is 2 to the power 4, 2 to the power 4 minus 1, which is 15, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this is a full binary tree. A complete binary tree says that all the layers must be, only except for the last layer, everything else must be full, and the last one should be what should I say? All the elements in the last layer, they should be on the left of the tree. So what I mean by that is, so if I want to draw, suppose there is a, we'll say we are doing a max heap, so it is 3 here, and we have got 2 here. This will be a max heap, only 2 elements. However, suppose somebody draws like this is not a max heap because this thing cannot be empty. Is my point clear?
Okay, so for a max heap, the left has to be there.
Yeah, so what we do is basically we start filling from the left and then we go towards the right. If we need, suppose there was, so here it was 2, here it is 1. Suppose we have another one, say 0. So it will come to the left of this one. Then it will go like that. And suppose another one comes, -1, -2, -3, like that. Another level, again, below that.
Max heap is always a binary tree. Is it always like 2 nodes only, at the most 2 nodes?
We are talking about binary heap right now. That's why every node will have at max two children.
Sorry, yeah, you mentioned that. Yeah, thanks.
Okay. Okay, if that is clear, so let's continue. Now let us.
How about the child node being equal, the value being equal? Can it all be same? Like 97 can repeat on the left.
Yeah, I think that is fine. Correct. If I'm wrong, if somebody else has more information, please share. But I think that is fine. As long as, so if there are 397s, you will find 197 here, one another here. That is my understanding.
Okay.
Okay. So should we continue then?
Yep.
Okay. So let's see. So there are a few things I wanted to describe. So we'll go in this way. People will always ask, is the binary heap, so okay, let me just show you the array representation of it. 3, 2, 1. In the array, we'll have 1, 2, and 3. You will see 3 will be here, 2 will be here, and 1 will be here. What I mean by that is, so if the parent's index is 0, then the left child will be at 2i plus 1. And the right one will be 2i plus 2. Suppose there was another one. Okay, so that will be 2 child, right? Like we were drawing like this. Suppose it is here. So the 2 child will be at 2i plus 1, which is 2 times 1, which is 2 plus 1. So it will be at 3. The right child, so the left child formula is 2 times I plus 1, and the right child will be at 2 times I plus 2. Okay, that is the index. Is this clear? So that is how, whenever you add any child, it is basically going to take, it is taking the next step, next index, next index, next index. So it is a dynamic array which is growing towards its right, like that. We will come to a situation where we'll see when we go to insert something. Suppose we insert 50 here. Now it is not a heap anymore. We need to basically percolate this up. It should go up. Sorry, this thing it look like 50. So in this case, what we say is, okay, this is 50, but this is a max heap. So let us switch these two elements. So 50 goes here, 2 comes here. Now 50 is checked with 3. Now 3 comes here and 50 goes here. Now we have restored the heap order property. Okay. So we'll get to that sooner or later. Okay, so I hope I made that thing clear. So this is a pretty important thing. So given a parent, how do you get its children? Conversely, if you have a child, how do you get to its parent? It is very easy. What you do is, if child index is C, the parent index will be C minus 1 divided by 2. I'm just looking at this guy actually, and it is an integer division. In Python, that is how you write. So it is 2 minus 1 is 1 divided by 2 is it will be yeah, because it is integer division, it will become 0. So like that, suppose it is 3 minus 2 is 2 divided by 1. So that is how, when we reach from parent to child, we can also reach from child to parent just by the simple computation. That is how we traverse from child to parent and from parent to child. I hope that is clear. I'm not able to follow any comments you guys might be doing. So if you just say something, that will be clear to me. Okay. So with that, I hope it is clear, and I'm continuing.
Yep.
Now, let us look at how do we form a heap. Suppose we are given an array of just some elements. How do we convert it to a heap? Because we know that the heap is also an array. So there must be some reordering we need to do. For that, let's watch a animation. This is a min heap. That means the minimum of the values should be at the top. But what we see here is, at the top we have got 31, which is the total 31 elements are there, and the top is 31, and we have got 1, 2, 3, 4 there at the leaf level. So let's check one at a time. So this is called heapify, and heapify is an order of 1 operation. I'm not going into that analysis. I don't know myself. There is the CLR book will have that thing, but I just wanted you to show how the heapify works. In languages like C++, we have got algorithms which can convert a given array into a heap. So we'll look into that. By the way, just for curious people, it is called make heap. That is an algorithm. Okay. Question?
No. I was just telling make underscore heap. Yeah, that's right.
Okay. So let's just take a few steps here, and then this will help us understand how a heap is created out of just a given array. So this is how the array is right now. And let's just go one step at a time. First step, we go to the what is that called, leaf, the rightmost leaves, and we compare. This is a mean heap, so obviously the one should go to the one should win. One is the minimum. So next step basically says we identified that the one should be compared with the parent. Next time we swapped, because 17 was higher than 1, so we swapped it. Similarly, we'll do for all these things. Let's see one at a time. 3 wins, 3 is compared with 18, swapped. 5 wins, 5 is compared with 19, swapped. 7 with 20, swapped. Like that, we go for the other ones also. So this is the build heap, or this is the make heap algorithm running right now. So now at this level, we have touched all these things at this level. So let's start, we have touched at all the things at this level. So let's start with this level. 1 and 3. Of course, 1 should win. Just repeat the same thing. Similarly, okay, when it came down, now it is basically, it is recursing into it. So we'll let it recurse. I'm just repeating the thing. So if I just continue to play,
And in the array, like, are we getting the level by how do we switch in between the levels? Like,
that particular algorithm you mean, switch between the levels. So as you saw, these things are actually contiguous. We started from the left, okay? We came all the way up to 0. So we started from these two, then we came back. I have not prepared that algorithm in my mind right now, so I'm just kind of guessing right now. So probably I can just follow up that offline. I have not prepared that algorithm. Okay. So, but it is just a visual representation of how the heapify works. And the heapify is an order of n operation. Okay. So I will just let it continue, skip forward. So at the end of the thing, we will have something like this. So this is the heap we generated. Now, the question is, people think a heap is sorted. No, heap is not sorted. As we can see here, after 1, we have got 9, then we have got 2. However, if you see, then you will see the mean heap property is always valid among its children. 1 is less than 9 and 2. 2 is less than 5 and 3. Things like that. So this is a partial ordering. This is not a total ordering. Total ordering is something you get when you are doing an in-order traversal of the binary search tree. So in our example here, suppose we this. Okay, so in our case, suppose we started with this 3, 2, 1. I told you that this is a valid heap, but it is not a valid binary tree, binary search tree. Sorry. In a valid binary search tree, it will be something like, okay, this is a max heap, but I did it wrongly. So let's do a min heap also. So for example, 1, 3, 2. This is a min heap, and the corresponding binary search tree will look like. So we are comparing heap versus binary search tree now. So as you can see, if you do a in-order traversal, you will get 1, 2, 3. That is 1, 2, 3. But if you do a in-order traversal, of course, you will end up not with a sorted. It is not a sorted array. So that's why whenever people think about heap, they always think maybe it is sorted. It is not. Heap is not sorted. So that is one thing I wanted to make. Heap is not sorted. Okay, let us start with comparison of operations. Why heap is important? Why should not we go for a sorted array? So let's, I'm just making this room here for me. Okay, so build operation, as I showed you, the make heap that we just now saw, that is order of n. In a sorted array, it will be order of n log n, right? Okay, insertion. Let us see how the insertion works in min heap so that we can see what is the difference between the sorted array. To see the insertion, let's check this guy. So we have a, what we have here is a max heap, and we are inserting 26. So we are going to follow how insertion works. First thing is, as you can see here, so this is a complete binary tree, but not a full one, because at this level, all these values are empty. So what we do is we add the new value that is coming in to the next available slot, which is the left of 45. So that is where we started. Now, of course, it is a Max Heap, but it seems like this thing is perfectly okay. But is it a Max Heap? Let's see. Give me a second, please.
Yeah, it's still a max, right?
Yeah, it is still Max. Correct. Okay. So 26 has been inserted. My bad, probably. It is not showing how the things should work. Okay. Okay, suppose, let me just try my, okay, I think I showed you, but let me just, very simply, I'll show you. So suppose there is a Max Heap. So I would say 30. And there is only one value it has, which is 20. This is a valid Max Heap. Now a new value is coming. Suppose 90 is coming. If the 90 is coming, of course, we'll start with the next available place, which is, this is our array. This is, by the way, abstraction. This is the actual implementation. This is actual how we store the value. Now, this place is empty, so we'll first put it here. That means it has got this. Now we'll check whether its parent is, this is Max Heap, whether its parent is really smaller than this, bigger than this. No, it is not true. That's why we need to swap. So this becomes 90, this becomes 30. And we'll do this swapping. This is called percolating up. The value is going up. The percolation will happen until we establish that the heap property is valid in this chain, this child to parent chain, until we reach to the root of the tree. So what I mean by that is, suppose instead of 90 here, suppose we added 25. Now next time, suppose we added 90. When we added 90, of course this needs to go here, but if we leave it there, then it is not going to be a heap. We'll have to take the 90 from here to here also. So 30 will come here, 20 will come here. That is how the insertion works. So looking at this, so one insertion can travel up to how many times? The percolate up operation can happen how many times?
Height of the
label, basically. And because this is a complete binary tree, the label is always guaranteed to be log n. Okay, that's why I can simply mention my insertion is order of log n.
So Rajendra, one correction here. So building the main heap also n log n, right?
Sorry?
Building the main heap also n log n.
No. So there are two ways.
Not just the order of n.
Yes. So if you are calling heapify on an existing array, then that is amortized or amortized order of n. It is not exactly n, it is amortized. All the operations together. So that is what I was talking about. So whatever all the operations that are happening, if you amortize them, basically kind of count everything and then add them up, that becomes order of n, amortized. But if you are building a heap like through the insertion method one after another, that is going to be order of n log n. because each insertion is order of log n, and you are doing n such operations. So there is this distinction I wanted to draw.
I did not get it actually. So how did it become amortization? I did not understand.
Amortization, I'm not also touching the amortization part. Please,
okay.
there are elaborate proof to
Okay,
establish.
okay, that's fine. No, I mean, if we take an example of this array which you have drawn in below, right? And then suppose we have n number of elements and we want to build a heap. So every time you pick an element and you decide its position, right? So deciding its position is something like an insertion into a heap, right? That's a
No.
n log n, right? Because you pick an element and you try to find what is the best place for it.
So
how we build the heap. That's what I
actually I'm not able to answer how amortized order of n it is. But,
okay, that's fine. That's fine.
Yeah.
But if you look at first, we go to the bottom level, right? That is n, right? And then when we're done with the bottom level, we go second to the bottom, which is n over 2. And as we go up, it keeps divide by half. And every time we go up, we touch at most one node, and the worst case, we need to percolate it down. Only one node going down. You see the whole tree, for example, 93. And now, let's say, that node is violate the property. And then, you need to push that node down, but it going down at most only like, 2 level right there. So it cannot be n log n.
What are you trying to, are you talking about building it, or are you talking about the insertion?
Building the heap, given we already know the, given array of all the elements.
Mm-hmm.
So like, the speaker mentioned, right? We do insertion one by one because we have to do that. So there be n log n. But if we have all the information, upfront, we initialize it, make heap, you will see that big of n. If you go into like, Greek for Greek, you will see that the proof it's log n. If you a C++ developer going to C++, the API that also show that it's log n.
Okay.
Yeah, I buy that.
Yeah, I think somebody has given that link which proved with that theorem, I guess, which is building a heap is big of n.
Okay.
There's some article on that. Yeah.
Perfect. In interest of time, can we move forward now? Okay. So, okay, I'm just doing a comparison between sorted array and the mean heap. So in the insertion, if you do a insertion to a sorted array, what is the time complexity? Okay, so what I'm basically trying to establish here is, if you have a sorted array, and how do I say that? Suppose I have a sorted array 1, 3, 5, 7, say 9, and I'm trying to insert, say 2 into it. What is the time complexity for this one?
Order of n.
Order of n.
Not log n?
No, it is order of n, because log n, you will come to the place where you want to insert it, but then you will have to make room for it, right? So basically you will,
yeah, okay.
so it will be, so that's why. So these are very interesting things which we overlook, but I just wanted it to be very clear here. Now, when I started thinking about heap, I was just thinking, why should not I take sorted array? It is already there. But these are the two things, if you look at it, then you will understand the difference between this thing. The heap is kind of a pay-as-you-go data structure. What I mean by that is, okay, before I do that, let us look at this one. In a mean heap, accessing the mean element, my mean element is always found where? at the 0th location, because that is the root of the tree, right? It is always there.
Yep.
So to access that, what is the complexity?
1.
It is order of 1. Okay. Similarly, in a sorted array, to access the minimum element, what is the order of that operation?
Same. Big of 1. Yeah.
Okay. So from that comparison, it looks like both of them are same. But there is this distinction. The distinction comes when things are here. When you are basically in the mean heap, when you are inserting or when you are extracting. I didn't show the extraction. It is just the reverse of that. That is also order of log n. I hope if you guys are not able to visualize that, then I can go to the extraction part. I think I have got an extraction. Let me run that. This is extract max. How do we extract it? Okay, let us run it. Not a big thing. So we are extracting the maximum element here. Let's see. 82 is extracted. Now what? We start with the last child. Okay, the last of the child, and then we check. We put it at the root, and then we let it percolate down. How does it percolate down? It has 2 children, and this is, I believe it was a Max Heap. Okay, so 67 and 70. Of course, it is smaller than both of them. Which one should go to the top then? It should be, of course, 70, because 70 will be greater than both 67 as well as 56, right? So that's why now we have guaranteed, now the heap property is satisfied. So as you saw, we started with, so to extract, we had to do how many operations? Basically level wise, if we count, we started from this level, then it went up. I mean, that was just a blind, basically you pull it out and just put it up the top. So that is order of 1. However, it had to percolate down all the way up to the bottom, all the way till the bottom. In this case, unfortunately, there is only one level it can go down to, and it stopped there. But take my word for it. So anytime you are doing extraction or insertion, it has to traverse through the whole hierarchy, whole layers. That's why it is going to be order of log n. Is that okay? Is the explanation okay, or anybody wants any more? Okay, so this extraction is order of log n. In a sorted array, what is the extraction complexity?
Open.
I can say O of 1 actually. It is just like O of n. Yes, if you want to basically shift everything back to the root, then it will O of n. Otherwise, we can simply, it is debatable, I would say. Depends on how you are using it. I'll just take it as 1.
Oh.
Okay, is that okay?
Yeah, that's fine. Yeah.
Okay.
Depends on like if you want to read it.
And ordering wise, we already discussed the mean heap is not a total ordering. It is not a sorted order. So that is called partial ordering. And this is total, because once you sorted, everything is, it is a sorted array. You can do whatever you want with this. So these 2 operations, if you look at it, not these 2, in fact, along with this one, if you look at it, these 3, basically heap is a pay as you go type of data structure. First of all, you are not paying log or n log n cost to make it. You don't pay anything extra over the sorted array if you are just accessing the minimum element, just one element. It is not a random access data structure. It just exposes only one element, which is at the top. But that is order of 1. Only if you want to insert or delete, I mean extract, then only you pay the price. So that's why it is pay as you go.
I'm a little lost on why extraction from a sorted array is O1 instead of ON. You don't have to shift everything over?
That's correct. That's why I said it is debatable. So let's keep it like this. Correct.
If you are extracting the
So I think the extraction here, basically the word is basically saying that that value is removed, not like I'm just indexing and just using it, nothing like that.
Okay, yeah.
Okay, so if you're indexing, it is order of 1, it is there. If you're not, I mean, you can always index into it I++, so it is gone, so to say. But if you are shifting everything, it is order of n. Okay, I think we are at the same page, no more confusion.
Can you explain why build is O of n and not O of n log n?
Sorry?
Can you explain why build is O of n and not n log n?
Okay, so there is a link shared in the chat room where that thing is explained better. I'm not going into the details of that. In fact, I don't know actually. So I'll have to skip this one. Okay. So let's go to the next one. So I think we have already seen the difference between binary search and heap. Okay, next one, how heap sort works. Heap sort is a very interesting concept. All it does is, okay, let us start with our simple concept. So let's take 3, 2, 1. Where are we? We are 3, 2, 1. Now, the way heap sort works is, it goes on continuously extracting the top element. And as we saw here, in the extract max, how does that extract it? It basically throws that out, then puts whatever is the rightmost leaf over there, then percolates it down. So let's see that. So 3 is out. It doesn't do it out and out kind of thing. Instead, what it does is basically it creates a temporary variable. It knows that it is going to use this value. It puts that in a temporary variable. So in other words, what it does is temporary variable holds this. Now, whatever is extracted is put here. Okay, so 3 is gone. Sorry, 1 is gone to the T. So it just makes use of the same place. It is called an in-place sort. That's why we'll see why it is an in-place sort. It is not taking any extra values. So now 3 is out and 3 came to the place which was vacated by the 1. We know that the 1 will go to here, and then we'll have to ensure the heap order, because heap is right now out of order. So what we do, we basically percolate down. By percolating down, we'll have to basically switch. This one goes here and this one comes here. So at the end of it, we will have something like give me a second, 2 and 1. So that is the heap remaining. Mind you, I'm not keeping the 3, I'm not showing the 3 anymore because that is out. So my heap size of heap is right now 2. In this case, let's again continue throwing out our, extract our max. So 2 goes out. Before 2 goes out, by the way, this thing also changed at that point of time. So I don't know how to write it. So suppose I write it like this, and 3 was already there. So I'll keep it like this. I hope you are able to follow right now. Are you with me? Somebody? Hello? Okay. I have no idea. No, so I'll continue basically.
Yep.
So yeah. So right now, because the 2 is removed, we'll continue and keep it at the next available. So 1 is right now kept at T, because 1 is the rightmost leaf. So 1 is at T and 2 is removed. It is extracted out and put it here. Okay. Now the T is placed at the root of the tree. And now, because this thing is removed, there is only one thing remaining, which is the root, and we are done. So at the end of it, we have got 1, 2, and 3. Now this is sorted. And as you can see, a max heap gave us a increasing sorted array. The complexity of this will be, how many operations we did? We did n number of extract max. That's why each n number of extract max we did, each extract max is log n. That's why heap sorts complexity is order of n log n. Okay, so with that was just a little background. I'm not going to go into any more details. If there is any questions, we can look into that, and then we can jump into our questions. Okay, so I'll take that as a, because of the time we have, let's go and check the questions now. If there is any questions, please feel free to ask right now. I don't know how to. Okay, nice. So the first question is this. Anybody wants to basically, so the question, I'll read it out. We have a list of points on the plane. It is a Cartesian plane. That means every point is identified by its x coordinate and y coordinate from the origin. We need to find out the k closest points to the origin. Any ideas how we can do this?
Yeah, I think there is some formula which you have to put on XY points and put it in the priority queue, and
Sure, sure.
Yeah, something I don't remember, but I think something on that line.
Sure, sure. So what I forgot who just now suggested that. So let us see any point which is given to us. Suppose this is a point given to us and this is our origin. Okay, so this is the x value and this is the y value. So how close it is to the origin is basically this is the distance from the origin, and this is just simple Euclidean mathematics says this is nothing but the square root of x square plus y square. Okay, so that is the value, that is the total distance from the origin, and we have got n such points here, things like that. So what is the idea here? How do we do it?
Find all the distances, like Sumit was saying, find all the distances and put it in array, sort it, or put it in a min heap.
Okay, yeah, we can, yeah, that is very good. Basically, we can just calculate all the actual distances, radiuses, basically, or hypotenuse, whatever you say. And then you need to keep a map for that then, probably, so that you can go back from the number to the whoever gave that, correct?
Yes. You need to keep the points as well, right? Not the distance, the exact locations. Yes.
Exactly.
Maintain, maintain all of these in a map so that you can refer back.
Correct.
And sort by the distance. Sort the distance.
Correct. Correct.
Oh, do we need a map over here?
Very good question.
Yeah, we missed it, but I think we want to return the points, right? Not the distance.
Yeah.
So we can make a queue like our priority queue or a heap like this that we can add, include based on like compare on the basis of distance and then add the points in that heap.
Yeah. Anyway, we need some kind of mapping between the distance to
Yes.
point of the distance.
Okay. What if we don't? Okay.
Could we simply, maybe every entry in the heap is like a triplet,
Yes. Yes.
and
Exactly.
then you just return the X and Y values and not the distance part of the triplet when you.
Yeah, I think there could be different ways of representing it, like a triplet, or you can create a class or a struct which will have
Yes.
three things. And, I mean, it's just an object at the end, which you can represent.
Basically, I'm just trying to create one structure instead of too many. But I guess you could do any approach. Yeah.
But for the heap, we only need a comparator, right?
Exactly.
So in that comparator, we can implicitly compare based on the distance.
Perfect.
We don't need to really, create the property for distance. I mean, a map or the class.
Yeah, that's what I'm saying. Yeah.
Perfect. Very, very nice discussion. So let us just decide. So because we are thinking about finding the k closest points to the origin. So what type of heap? Okay, sorry, but I thought maybe we were gravitating towards heap here. So I'll just take it forward with a heap. But now my question is, what type of heap we are using? Is it a min heap or a max heap?
Min heap, because we want closest, right? Like the shortest distance.
Right. Okay. That is very good. So if we are doing a min heap, anybody wants to volunteer to just try?
Okay. Is that the min heap or the max heap? Like,
min
heap. I think it could be the
no. Let us keep
max
it simple.
heap, right?
No, it has to be a data structure which will basically
If you want to find the the smallest distance quickly, you want to start from the root, then I guess you would want a min heap.
I think it should require a max heap.
Yeah, because we want the heap to be size k, right? So if it's greater than that, we don't want to keep that.
Okay.
Let me see. Oh, maybe
because
the min heap. Yeah.
Okay. Because everybody is now getting confused. Let us not get confused. First of all, let's keep our requirement very clear. We are basically trying to find out the k closest points to the origin. Whichever is closest to the origin will have the minimum, will have a distance which is less than the other points, right? So what I mean by that is, so if this is the, how do I do it? If this is the origin and this is a point and this is yet another point, this is the closure point. How do we know it is closure point? Because the distance is less. So of course, if we are having a min heap, then the first one that comes out is the closest. The second one, the next closest. So min heap works. Is that correct?
Yeah, but that way you need to put everything inside the priority queue, and you pick it one by one out.
Let me take the next step now.
Yeah.
What
I mean, the problem is if you use a max heap, you don't know which of the leaves at the bottom are going to be, let's say your last level has, let's say it's only 3 levels deep and there are like 4 terminal, terminal nodes or whatever you want to call those. But you only want, I don't know, maybe your K is 2. So how do you decide which 2 to return? Because you're not guaranteed. There's only some information that.
Okay, so let's.
So in example as well, over here, if we say that we want to return K2 and we have 3 inputs, how we are making sure that which is the minimums? That's only possible if we remove whatever the maximum distance in a heap is there, because we are sure that we don't require that.
Right, so that's why I'm saying max heap won't work.
Max heap would work, I am saying that,
okay.
because we'll be removing the maximum distance from the queue which is having so our root would be the maximum the node which will have the maximum distance. So because we don't require, and whatever the left in our heap would be our answer.
I think it
Why do you want to go through the process of extraction multiple times?
I think we can take an example and go through it. I believe that it can be solved by both the method, but
yeah,
the underlying logic will be different. But you can take either of them, it will work.
So let's do one at a time. So let us just think the concept first. Sonia, do you want to basically show how the Max Heap concept is going to work?
So someone wrote to use a max heap and put only k points in at a time.
right, yeah.
Okay, so let's think about that. Suppose our k is 2 and we are basically keeping a max heap. Okay, so first we have a max heap of length. How big the max heap length will be?
K, size K.
K, and our K is 2. Okay, so, or in other words, we have got only this type of a heap here. Okay, now let's see. We have been given an unordered, it is just a vector, there is no order, right? Whatever comes, we are just going to put it. Okay, so how is the max heap going to work? The max heap, we know that the top of the heap, the top element is the representative, that is the leader of the heap. Okay, so if this guy, so we need to figure out, there are total, we have got 3 points to choose from, and we are choosing only 2 of them. So let us start, and whatever we get, suppose we got 2 first, we'll put 2. Then we got 3, so we'll put 3. Because it is a max heap, and it will, yeah, so it will look like this, correct? This is a 2, by the way.
That's correct.
Okay, now comes 1. What do we do?
Just put 1 into the heap and remove the max.
Okay, exactly. So that way, so we basically throw this out. Why? Because we have now our heap is at maximum capacity. Right. We wanted only 2 value here, and we have got 2 value. Now we are in the choosing mode. We are choosing to keep what to throw. So now 1 came, which is better. So we keep 1 and throw out 3. So now we have got 1 and 2 in the heap. Okay. Now we can simply say we have got the best 2 items in our heap. So that is using the max heap. Is that okay? Is that going to work?
No, Rajendra, I think we said this is a max heap. But have their min heap, right?
I mean, yeah. After inserting the 1, I didn't shuffle that.
Yeah, the last heap be faster, but it would be 2.
So this is how it will look like, right? After inserting the 1.
So I mean, that means we are saying like max heap also will work, because max heap.
Yes, correct.
So you're just removing the root node each time you're over capacity.
Yeah. So what we are basically saying is, using a max heap, we try to push into the heap until the size is equals to k. And once we have the saturated size, we are in the choosing mode. We'll have to remove 1 and insert this one. So
what if it's min heap here? We would have, if it was a min heap, we would have removed 2 and inserted.
If it is min heap, we will simply keep removing, keep removing k elements. That's all.
So you would basically just build the whole thing and then take the first k elements.
Exactly.
You will have to add all the elements points in our in our heap.
Correct.
If there is n, if that size would be, I think, n, then of heap size would be n.
That depends on the question, if the vector that is given to us, if it is modifiable or not. if we can modify, reuse the given vector, then we can always do a heapify over it. That is order of n amortized. And then we can simply extract out k elements. So they will come out in the order. The closest one will come out first, then the next closest, then the next closest. Questions?
So basically the size would be, if we have given like n size of the heap is, and then our, while we are, for example, heapified, that would be also n.
Yes, correct. By the way, the n is the best conceivable runtime because we'll have to check each of the elements in the vector. We cannot simply, we cannot get anything better than that. Order of n is the best it can go to.
But
Otherwise,
but then you have to do, there's obviously some, log something, either log n or log k for the heap itself, for some of those operations.
Correct.
So how do you get just n for?
No, we are not getting n.
Okay.
I didn't say we are getting n. What I'm saying is basically this make heap is not making our solution worse either. That's what my point was.
Yeah.
But the catch point was the given vector was modifiable. If it were not, and if we have to take additional space for the heap, then probably we should choose the max heap. If the vector itself is modifiable, then we can simply reuse it. That's what my point was.
So it sounds like, is this a consideration that is language specific? Because like I don't write in C++, so.
I like C++.
Actually, this is, I'm kind of making a point about the heapify operation. I'm counting on the heapify operation that we discussed here, the build operation, order of n amortized. That is what I am basically trying to point out.
Yeah, I think to your question, if it was like,
you're saying if the vector is modifiable, so that sounds like something language specific.
no, if it is const, right? If it was const, then you cannot modify it, right?
Are we talking about this particular solution?
No. Yeah, in this solution, the vector we passed, we are saying like we are modifying it, right?
Correct. This guy modifies it right now. Yes.
The question is this C++ specific to be able to modify? I think if the function declaration has a constant in it, you would not modify it, right?
So yeah, there is two ways. One is the requirement is given saying that don't modify the input. And second is if the language we can, basically enforce that the parameter that is passed is non-modifiable. So each language has their own way to say that, right? Okay. Parameter pass is non-modifiable. And another one is requirement itself saying that don't modify the input. I mean, somebody told you or whatever way, it is not enforced, but it is told. It is the requirement.
Okay.
Perfect.
So for this solution right here, I mean, how do we handle the integer overflow?
Where is the overflow happening?
In the comparator.
Oh, that is a very good point. Yeah.
In the I'm not on LeetCode right now, but in the requirements or like in the they usually provide some details about what the input will look like.
Yeah, so input is maximum 10K.
Yeah, okay. But like in the real interview, if they go extra step, then if it's quick, you can tell me. Otherwise, I can.
Yeah. Good. Yeah, as somebody pointed out, so this is basically ensuring the this thing that doesn't overflow. Good point.
But in case it overflow, then how do we?
They haven't given the condition. Would this?
I mean, the interviewer
that will be a different problem to solve, I guess.
Yeah.
Is that a quick twist that we can do that, or? need consider amount of time, then we can skip it.
I think there is no other way, because we'll have to anyway compute the x square plus y square and square root of that. So unless there is some mathematics library or big number library, big integer library, probably.
Okay, yeah.
But you can use long in this case, right? So that should be fine.
Yeah.
Yeah.
So
I mean, we can always get the input that will always,
that is not a big thing. Yeah.
Yeah. I mean, we can always get an input that will, the long log is not sufficient for that. So you can never say that.
Okay, perfect. So should we move on to the next question?
Yeah.
Okay, let's go. So this is. So the question is basically saying we have been given a list of meeting intervals. We'll have to find the minimum number of conference rooms required for this list to run all the meetings. So if I go to example 1, so suppose, of course, this needs one meeting room. While it is going on, another meeting is starting. So of course I need another meeting room here. So that is 2 rooms. Now this thing is saying one is starting at 15. Even though this one is running until 30, this thing has, it was done by 10. So we can reuse this meeting room to host this meeting. So the total number of meeting rooms we need is 2. Is the question clear?
Yes.
Yes.
Perfect. So how are we going to do it? Okay, I mean, please think about it. While we are thinking about it, there is one thing I wanted to point out. So personally, I feel using a heap is kind of beautiful in the sense that it takes a lot of cognitive burden from you. Why? Because it is a kind of a collection of elements. Only one is visible. The top element is visible, which is always guaranteed to be either max or min, depending on what type of heap you built at the first place. And you cannot fiddle around anything in the middle. You can add it. You can add an element. It will automatically percolate up. You can remove the top element. It will automatically rearrange itself. Only when you make any modification to the structure, you pay the price. Otherwise, you get the best element, the leader element, at the top place, always order of 1. So that way, basically, it takes a bunch of cognitive burden from you. Let me describe what I mean by this. Suppose this is a meeting going on. Then in another room, we started another meeting. Now when the new meeting is coming, it will have to go and see, first of all, how many meetings, how many individual meeting room, how many individual meeting rooms are running concurrently, out of which meeting room is going to be over soon. All this cognitive burden will go away if we use a data structure we are discussing today. Anyone want to try? Anyone want to try, please? Give me something.
I think probably a visual representation would.
I don't want to try because I haven't practiced with heaps in my language, so I know the syntax. But the approach I would take is to do you want the top, the root node to be, the root element of the heap to be the meeting that has the earliest ending time.
Perfect. Mm-hmm.
And then when you, from the input, each time you come to a new meeting, or, you know what I'm saying, a new tuple, you want to compare the start time, sorry, you want to compare the start time with the end time of the root the root element in the heap.
Okay.
That way you'll know if you can pop out the.
Perfect. I think I got your idea. How about others? Did you guys get the idea, which just now the speaker said?
Yeah, I got it kind of, but I was just thinking, like, why do we even need an heap for this question? Like, can't we just traverse through, like, I start with my first time, which is 0 to 30, and then I go to, it is like a list of lists. So I go to 5 and 10, and I do a similar check with the start time and the end time for the one which is already there in the list. So I make a call like this will need one conference room, right? And when I go to the next one, I can, I mean, maybe that is n square, I think. I have to go through each of the each of the meeting time in the
Would you agree that getting the root element from the heap is just O1?
Reading is O1.
Yeah.
If
So
you're extracting it, then you're paying the price.
Okay, but you need to read it each time, because the we don't, right? I mean, you're going through if there's n elements in the input, then you're gonna be checking the root element in the heap n-1 times. So we want that to be O1, if possible.
Correct.
I mean, you're making some comparison.
We just walk through an example.
Yeah. So this is the example I was working through. Okay. Which example you want? Sorry.
Yeah, one if I just do it on the whiteboard. Because initially, what do we put in?
So this is the input, right? Are we discussing something else or this one?
That one.
Okay.
Okay, so there is something I forgot to mention is we'd actually have to keep track of the maximum size, the largest size that the heap gets to.
Okay, nice.
Yeah, so I forgot to mention that.
Okay.
I mean, there may be other approaches, but the one I described, you'd have to keep track of the maximum size.
Okay.
So if you did 0, 30, that would become your root element of the heap. And then when you get to 5, 10, you're going to compare the 5 with 30.
Anat, do you want to draw? I don't know how to give you control. I can give you control.
Oh boy.
No, anything. That's fine.
Is everyone following? Because this is a small example. That's why I'm. So 5 is less than 30. So we know we can't use that room. We're going to.
Maybe Rajendra, you can draw.
We're going to keep that, and we're just going to insert the 5, 10. And then so you're gonna say, okay, there are 2 rooms being used, so we're gonna up our number of rooms to 2. Then we're gonna get to 15, 20. So when you inserted the 5, 10, the ordering is going to change so that the root element of the heap becomes 5, 10, and 0, 30 ends up being pushed down.
So first of all,
the reason is because 10 is less than 30.
So we said that the heap is a mean heap, correct?
Yeah, minimum based on the second entry in those tuples there. Yeah.
Okay, nice. So if let me just write that. I thought somebody will take over and I'll just sit and watch. Where is my, oh, is it already? I can write it. Okay. So when we are entertaining this one, so we have got 30 in the heap. Oh, I'm not able to write it. How do I? So yeah, and maybe the annotate. Give me a second. I don't know how to write now. Erase. Okay, let me start again. Annotate. So when we are handling this guy first, so we have got 30 in the heap. Okay, now what are we doing?
Well, my trick would be to actually insert the whole tuple, but I get what you're doing.
Okay. Because so, we are only comparing this guy, so I just pushed that one only. Okay. Then.
Okay. Yeah. So then from 510, we're comparing the 5 with the 30 because we need to know if we can start the meeting. So yeah. 5 is because 5 is less than 30. We can't remove that room. Right. We have to just insert the item. Okay. So now we're going to insert that item. So we're inserting 10 into this min heap. Yeah, and it's going to end up at the root because it's the smallest item. Okay. So now we're keeping track of the number of rooms. We have 2 rooms being used. Now we get to 15, 20. We're comparing the 15 with the root element, which is 10. 15 is more than 10, so we can actually remove 10.
Okay.
And then we'll insert that, and we're actually inserting 20, not 15. We're inserting, yeah.
Okay, nice.
So the number is now we've exhausted the input array.
So this is also 2.
So we see that the size is 2, yeah.
So the maximum so far is 2. So there is nothing we are changing. So this is our return value. So this is very nice. This is exactly the algorithm I was also thinking. If there is any other ideas, then we can think about that.
Well, it's not going to work on example 2, right? Because if you put 7, 10 in.
So let us start with that. Anat, do you want
we can see, maybe it won't work. I'll check. So 7 and 10 would go in, or basically the value you care about is the 10. And then if you look at 2, 4, you're comparing 2 with 10.
And 2 slash 10, so you add 2.
So we'll add 4 here.
Okay, yeah. So here's my issue. It looks like the input is not ordered by the start time. Yeah. So we have to do that first, I guess.
This one was ordered actually by the starting interval, start time, but this one is not. That's why it tripped us. Correct.
So, I mean, if you have to do that operation first, just, if you want to sort it by the start time first.
So we'll just reshuffle the input array like this. Okay. Then we'll start the processing like we did. Correct. So this is how it will look like. I mean, I'm just changing the order. 2, 4, 7, 10. It doesn't look like 10 anymore. But please believe me, it is 10. So 7, 10. Okay. So this is how our input should be, so that we can use the same technique to basically come up with a result. Correct?
Yeah. Yeah. So if you want to use this approach, you need to ensure that that your input is sorted by the start time.
So Leon, is it going to work?
Yeah. So if it if it equal, we also pop it out, right?
If it is equal, we'll pop it out because we can use the same room. Correct.
Okay. Yeah.
Okay. Anybody wants to attend it? Try.
I think you might also have to, if you're going to sort the input first, if you have 2 elements with the same start time, I think you want the one with the earlier end time to come first. I'm not sure if it matters, but
okay.
it may.
For me, it didn't matter though. But that's
Yeah,
the
one thing I wanted to
actually.
Yeah, one thing I wanted to check, like if we are using heap sort data structure, then why do we have to sort the array upfront, like the sort the input upfront? Wouldn't the heap sort?
For this reason, right? We saw this part.
Sorting on different things, like the heap. When you're inserting elements into the heap is just keeping track of the end times for the meetings. Mm-hmm. But when you sort the input, you're actually sorting by the start time. So you're sorting on different things. You can't use the same heap for that. Can you?
I'm not sure. I'm gonna have to maybe draw it and try again. Because I haven't solved this problem with the heap earlier. I solved it like just by using list. Definitely I have to sort this array with a start time, but I did not use heap for the solution.
You don't have to use a heap to solve this. But
correct.
I think it's nice to, I don't know.
It basically takes away your mental burden. That is what my point was.
So doesn't it help in the complexity perspective if we use heap?
It doesn't, in the sense that if you're not using the heap, then you'll have to repeat the checks, as many times as you are processing the next element, you'll have to basically repeat a check for each and every one of them, right?
Yeah, whichever you have processed before, you have to go through each list again.
Yeah, so that becomes so for every element, if you start comparing everyone before him, that is n square right there. So because we are sorting it, our higher bound is already set to order of n log n. Okay. Anything up to order of n log n, fine, but n square is not fine, correct?
I guess it depends on the problem, but yeah, I think that here definitely it makes sense.
Okay.
So I have another example. Can we walk through? So like 2, 5, and another one is 2, 5. Is that gonna give us 2 room?
Give me a second. I don't know.
The start time is 2, the end time is 5.
So what is the question?
The input, the start time is 2.
Give me a second. I think how we do it.
If you have 2 separate meetings that have the same start and end time.
Yeah. That should be 1 room, right? Oh yeah, that should be 2 rooms.
Because you're going to be comparing the end time of the second element to the start time of the first element. So I think it'll be okay.
So we need 2 rooms in that case.
Yeah.
Okay, that's fine. Yeah.
And so how do you decide with the heap size? It will be dynamic, because in this problem, we don't know if we need a heap size of, is it like maximum number of input what we have?
No, we don't know what is the heap size is going to be. It is dynamic.
It is
dynamic. Yeah, that's what he's saying. Like you don't know, like conceivably if you have
n log n, okay.
Conceivably if your input is size n, your heap could end up being size n.
Okay.
We are not setting anything up front because we don't know. And actually the size of the heap is what is giving us the actual answer. How many individual meeting rooms we need. That is the answer. Mm-hmm.
The only thing is it's conceivable that, maybe there's some point in time when you need, I don't know, 3 rooms, but by the time you finish going through everything, you've only got like, let's say 2 rooms open.
But yeah, but because
you need to keep track the maximum size that the heap ever was.
Exactly, correct.
Yeah.
At any given point of time, you needed 3 rooms. Of course, we need 3 rooms. We cannot go below that, correct. So anybody wants to try this? By the way, one thing I want to point out, the crucial heap operations is the comparator function, because all of them are basically they need custom comparator. because we are putting the, okay, sorry, my bad. The previous one was the custom comparator. This one is not a custom comparator, but I wanted to point out something. In C++, if you want to have a mean heap, then it is contrived in the sense that you'll have to pass the greater function. If you pass the lesser function, then you are getting a max heap, which is by default, which is the default in C++. Just wanted to point that out. I know Java is just exactly opposite.
That's very counterintuitive.
I know. Okay, so if in interest of time, we'll just move forward. So we discussed, so I just keep a priority queue. All I'm keeping track of is the end, meeting end time. So just one integer, and it is going to be a mean heap. Okay, that's why this thing is there. Then we just sort the given interval so that they are ordered by the start time. Okay, so this one will be taken care by that. 2, 4, and then 7, 10 will come. Then all we do is we go over the intervals one after another. If the priority queue is, if there is nothing in priority queue, of course, there is nothing we can pop out. If there is something in it, then we check if the end time, because priority queue is keeping our end time, if that end time is less than equals to the incoming one's start time. This is the case. If it is so, then we can reuse that meeting room. We can throw that value out, put the value in. Okay. So this point is clear, I believe. Okay, I'll just continue. At any given point of time, we are basically checking what is the size of the heap. Because the heap is keeping track of how many concurrent meetings are going on right now. Anytime, so this is the maximum we can get. So we are basically taking this. So this is kind of writing return value equals to math.max of return value or PQ size, and then return it. That's all. Questions?
But can we not do that at the end, out of the for loop? Just return the PQ priority queue size?
No, we cannot.
No, because the size could be smaller than the largest size it ever was.
But we are throwing the element out, right? Like at pq.pop, so that will not reduce the size of the heap.
It will, but
if you throw an element
automatically
out,
take care of that piece, no?
But what if this condition is not satisfied? Then we are not throwing it out, right?
Yeah. So really what you want to know is, so if for every element you've thrown out, a room has been reused.
Exactly, yes.
So basically, however many you popped, that's how many less than n.
I think can be done that way. Yeah, but yeah.
Yeah, so
you can just comment out and then say PQ side. That will also work. Yeah,
yeah.
That's fine. Yeah.
That's another way to do it. It doesn't really matter how you do it.
Yeah, that's fine.
Was it if line 11 should be a while loop?
Not needed, because we just, any incoming meeting only needs one meeting room at any given point of time.
Yeah.
Yeah, but like, let's say, right now the begin time is 15, right? But the top could be multiple of them, right? At less than 15. So wouldn't that go into the while loop? You keep popping out? Because let's say you have, the end time of our previous element, is less than 15. So you want to pop all of that out, right?
But
not only one.
You don't need to pop all of them out.
So if you pop them out, you get a smaller room.
Doesn't matter, right? at any given point of time, if we decided that we need maximum 3, we have already noted that down. Now we are reducing down to 1 or 2, it doesn't matter. As long as we are reusing it, we are fine. That's what we are doing. Yes, absolutely. If you want to exactly follow how many rooms are currently in use, then probably we can use a while loop also. But for this problem, it is immaterial, because the maximum is what we are already always interested in.
Yeah. Because I couldn't find a case, but could there be a case
yeah,
that?
So I see what you're saying, but we don't care how many are in use right at a given moment. Like we don't care at minute 13, how many are in use, right?
Exactly. What Leon is saying is very accurate, but at the same time, we don't want to be, because anyway, we're interested in the maximum value here, not the minimum. Yep.
Okay.
Okay, so let's go to the next one. So is the question clear here? So the question is basically, we have got some number of lists. Each list is sorted in its own, it contains a sorted list of integers. And we'll have to merge all of them, merge all the lists. How do we do it? Ideas?
This reminds me a little bit of the last problem we just did, where you're sorting the elements that you go through. Like we're not guaranteed that right now they're sorted. You see 1, 1, 2. If you go down the column,
okay,
like the first element in each list grows, but we're not guaranteed that, right?
Correct. If we just reuse this one, then it will not be sorted anymore. Correct.
Yeah. So you could have a heap where when you need to insert the next element, you're comparing that first element to, oh gosh, I'm confusing myself, but basically,
okay, let's do this.
One of the directions that you care about is the 1, 4, 5 direction, and the other direction you care about is 1, 1, 2. So
okay.
Gosh, this is sort of like how in the last problem we were comparing the start times in one way and then the end times in another. You know what I'm saying?
Yeah. Okay.
Okay. Aye.
So one way you could do is, take all of these one by one and just push in a priority queue.
Do we need to?
Yeah, that is one way.
Okay. Let's think about a better way. We have a better way.
Yeah, you can use the first elements of each and every.
Exactly, because they are the leaders here already. They are the minimum people. So if we just handle those elements first, so if we take a priority queue of only 3 elements, then that is good enough. Whoever we consume, suppose we picked, this one got picked. Okay, we'll just put that in our output and we say, hey, whoever is your follower, can you please push that into the queue? You are going out, can you push your follower? So now we have got 1, 3, 2 to handle. So of course, the next round 1 will be picked up. It will bring 4. So it is just like a, what should I say? It is, you see what I'm saying basically? How the problem is repeating itself. We are sitting at a heap, just popping out one after another. So that is what I meant by the beauty of the heap. You won't have to bother how they percolated up through the chain, that array, how they jumped through the hoops or to reach to the parent, nothing like that. It is just a heap and the top element is removable. That is the only thing we care here. Got it. So with that, what is the idea?
Yeah, you take first the 3 elements because there are 3 now, right? You put in a priority queue.
Right.
And then you start another iteration you just monitor the priority queue, right? So you pick up the first one, as you said, if it is a, now, this is going to be a mini heap for sure.
Right.
So then you pick up the first element, that will be the least one, put it in the output. And then when you put that, you look for that element's next one. That is what you said, right?
If it
So,
has
yeah, because it's least, so you can easily find that. And then push that in the priority queue.
Okay.
Yeah, but you could, so do you have to remove the element from the list? This takes some time.
How about this? If we just use our custom comparator to be aware of the list itself, then how it will be?
So one thing is that in a heap we can put index from where we are reading, and which list we are reading, and then yes, we can use custom comparator to compare those index to figure out whether it goes up and down.
Yeah,
that is one way.
I think that we can only need to put the head of each list to the priority queue.
Exactly. Very nice. Yeah, that is a very good one also. Yes. So every node of the list is itself basically keeping track of who is coming next, right? The node of the linked list itself, if we can make a heap of the linked list nodes itself with a custom comparator, would that work?
Yeah.
Yeah. So your custom comparator is just whatever is at the top of the heap, you remove it, but then that dot next is going to be what you push down into the heap.
Exactly. Yeah, that is the next node, right?
So use something like a pair of index or.
Very nice idea, Santosh. That pair idea. Do you think we already have a pair in a linked list node?
Yeah, I thought that it's set up that way.
The linked list node is a pair already. It has a value and a next pointer. It is a pair.
Okay.
Okay.
Yeah.
Perfect. So anyone wants to just try?
Second go up and then you go for the next one.
We've got 20 minutes and we have got a solved answer already. So there is nothing we are going to lose now.
So something that's really nice about this is your heap size will never be more than the number of lists in the input.
Correct.
So even if each of those lists was very long,
yep,
it would still be only size 3.
Right. So the way
at the end, how do we know? Let's say, so if a heap size is only 1, then we just append the whole thing to the result, right?
Until the heap is not empty, we continue. When the heap is empty, we are done.
No, if the heap size is 1, that means there's only 1 list. Then we just go ahead and append it, right? Okay. We don't need to keep going one by one.
Actually, if there is only 1 entry in the list, then why do we even create the heap?
No, initially that could be like an list, right? But we keep reduce it down. So at one point, the heap size is only 1. Does it make sense?
Yes, correct. That's true.
Yes.
So you are saying, like, if I have a priority queue with a custom comparator, something like a pair, and the pair's first, what do you say, the element will be integer, which will be actually the value, okay? And next one will be the least, what do you say, a pointer to this list.
Correct.
Okay. So because why we use integer here? Because if we use a min heap, that it will be compared with against that value, right? So whenever you push something, that is the reason you will have that value, which will be the least one on the top. Right. So first you actually do for the first three, okay, push that in the priority queue, and then you keep on iterating with the priority queue every time. And you pop the first element, okay, and you know that the first element has the second pairs, whatever that value will be the least pointer. Okay, so then you can use that next element to populate for the next element of that list, right? So in this case, like you have 1, 4, 5 and 1, 3, 4. So you push one and this list, whatever that L1 dash, and another L first and L2 and second and L3, right? So when you're actually iterating through the priority queue, so you will come up with this element. Yeah, so in this case, now you are having, yeah, if you come up with any one of them, you just pop it out. And yeah, then you can form another pointer. You can just point that list, which is going to go to something like a head.
Yep. So how about this?
Uh-huh.
So, suppose when the top of the heap, we don't know which one it will select, based on the value it will select, but whatever it selects, we know that that one will have to put in our output queue, correct?
Right, yeah.
And when we are removing it, because it is a linked list node itself, of course it has a next pointer, which may be null. But so if it is not null, then that value must again participate in the heap.
Yeah.
Yeah. If it doesn't have, then of course I have nothing else. Just give it. And Leon, as basically he said, as soon as the heap size comes down to only one value, which will happen here, we simply return it. We simply return that thing. There is no need of churning through the heap anymore. I didn't take care of that.
You don't want to say as soon as it has only one value, because the first time you insert, like the first time you put it in, it's going to have only one value.
No, for the first time, you'll actually put all the first elements of each and every list. So then you'll always have some value, right? Not one.
Yeah. So the point is that you cannot, I think what Leon was saying is that if your input has only one list in it, then there's no point in the heap.
I mean, the first, initially there's n list in the priority queue, and later, reduce down to only one list in priority queue. Then we can, stop there. We can append it.
The thing is, the priority queue is not actually keeping track of lists. You're only inputting the individual nodes.
No, actually, we'll have to do both, right?
So basically what we are seeing is, we don't care how long the lists are. We are in the priority queue. We are basically checking how many rows we are considering right now. So if the rows finally, for example, 2, 6, if it were instead of 2, 6, if it were 1, 3, suppose, then it would have finished before, right? We would be comparing only these two going forward. So
that's correct. But the question is how. The question is how you can only start checking this after you've input everything into the heap from the input array.
So what we'll do is, we'll first create the stage for the heap. Heap is our staging ground. We will onboard all the head elements of the lists onto it once. So that is where the heap is formed. So that is out of the loop. Now the loop begins basically. We go through we see which is the top, and then if the top is removed to the output queue, then the top gives us the next that participate in the heap. Like that it goes. Is it clear?
Yeah. So I think a great test example would be to have an input just of size 2, where one of the lists is like super long and the other list has only like
correct.
If we wanted to prove that it works for that.
Yes, correct. So one of the how do we do that? I don't know. Yeah, that's correct. So, so should we do that? We have got only 10 minutes. Anyone wants to try? Okay, I guess then let's start checking this one. So what we did is, so this is where we are basically creating the setting of the priority queue. Let me make it bigger. So first of all, this is the custom comparator. So this is the pair, Santosh, that you referred to. So this pair already has a value and the next pointer. So this itself is the pair.
Oh, so you're using a single list one, yeah. Okay.
I mean, that is what I got, and that I saw that is the pair itself.
Yeah, that makes sense.
Yeah. So priority queue is created, and this has to be a mean heap. That's why, because it is C++, unfortunately, I'll have to write greater than convoluted. Okay. Now this is the place where we are setting up the priority queue. Basically, the number of lists we are basically setting up the priority queue. Here we are setting up the output channel. So this is the normal linked list. When we are about to append to the linked list, that is what we do, right?
Dummy node, yeah.
Dummy node, yeah, dummy node with the right value. Then we have this runner. Now comes the interesting part. Until the priority queue is empty, look at the top element. Of course, we'll throw that away. We'll remove that from the priority queue. That is a different thing. We append that to our output channel. We update our output channel for the next iteration. If the top element has anything, any value left, then we push that. Otherwise, so if we don't push it, then that is how the priority queue becomes smaller and smaller. Okay.
Yeah.
So I'm not checking that special case of priority queue size is 1. That is one improvement that Leon suggested. Yes. So once I'm done with all that, because all these things are getting merged into the last one, okay, I'm basically closing that open end and then returning the value. That's all.
So to check, in order to check Leon's case, you could just on line 43 itself, you can add that, right?
Yes.
Just add pq.size, something like that, yeah. Yes, I will
In
have
that case, I cannot simply say null.
Yeah, you can't say that then, yeah.
I have to see whatever is remaining.
Yeah. Why are you doing both not empty and size not equal to 1? Can't you just say if the size is, if it's empty, you can't do dot size?
He wanted to compare that Leon's
I was
case.
adding the optimization for Leon's case.
Yeah.
Sorry, I didn't hear the last thing you said.
So Leon said, if the priority queue has only one input, one chain, then there is no need of having.
I agree, but what I'm not understanding is, so you originally put in an extra part of the condition, which was size not equal to 1, right? But couldn't this whole thing just be while the size is more than 1?
Oh, okay. Yeah. Yes.
But I just don't know if you can do dot size if it's empty. Will it allow it?
While priority queue size greater than 1, that's
This
fine.
should also work, yeah.
But then we have to say this one will have to fix. Right?
Do you want to do that? You can just ignore it, because anyway you'll have some value, at least one value, right? So you always go in 44 line.
That is a very good point. Yeah, whatever value is there, yeah, we can
just eliminate it. Yeah.
Let's see what happened.
Oh,
this is the wrong answer.
So what's the, so why did it skip the last?
Yeah, because when the size is 1, you have to take care something like 45.
Yeah.
Right? You have to, but you don't do it, so let's skip it.
So we'll have to say, because it is, if it is 1, then there is something remaining which we need to push it. So basically that will be.
Problem is then what happens if there's 0?
Huh? That
Like,
will be PQ dot top. Let us see. So
let PQ dot size equal greater than or equal to?
yeah, but like PQ dot top will, what's it going to be if the input doesn't have anything in it?
Right. If PQ dot size is there, then P next is this thing. So that's what, right? Greater than 1 means, so when it returns, it can be 0 or 1. If it is 1, then we need to do this. Otherwise, this thing is crying. This thing is not happy, correct?
Well, okay, but if there's nothing, so if there's nothing, then we need to set it to null, right?
Yeah, it is already null, right? So for example, this guy, if it is ending, that means it is already having null. Is not it?
No. I'm saying, imagine that the input has nothing in it. So you'll never get through this while loop. It'll just skip it. Then what happens?
Oh, you mean there is nothing in the lists? That's what you're saying?
Yeah, so you want to actually return this -1, or do you want to return something else?
Where is the negative
Return
one? I'm not returning -1 ever. I'm returning next.
Oh, and next will be null.
Yeah.
Guaranteed. Okay, yeah, good.
Yeah, I think it worked, right? Yeah.
Yeah, it worked actually. I just not submitted.
Yeah.
So that worked.
Yeah, good.
I think previously someone was mentioned, if we keep doing the dummy like that it may run out of memory, right? Because when we return next, but actually the dummy is still, in front of the result.
Dummy is a local variable.
Is that local?
Yeah, it is local.
It's a local.
In the stack.
Okay.
Okay. I think that's all I had for today. Bhavesh, if you have any questions, we can. I don't know how to close, so we can discuss or whatever you guys want. I hope it helped. Or do you have any questions about the concept that we are discussing?